So thank you for inviting me. I'm really pleased to be here and to share this session with Bins and to give you an overview about the malformation of the corpus callosum. So it will also give me the opportunity to present you the work that we have been doing on the subject during the last years. And actually, I moved last year to Essen in Germany, but I should say from now on that the work that I will present have been done mostly while I was still in Paris. So I will try to represent both France and Germany, do my best to do it. So first, what is the corpus callosum? The corpus callosum is the main commissure or midline structure connecting the two cerebral hemispheres in placental mammals, so also called eutherians. So it means that it's present in the mouse, in humans, but not in other mammals like marsupials or monotremes or in other vertebrates like fish or birds. It's composed of 200 million of axons that are highly myelinated, and for this reason it appears as a white matter structure. So let's see if I can use my own corpus callosum to use the pointer and talk to you at the same time. So here you see the corpus callosum. It's a white matter structure. It's a sagittal section of a postmortem brain. You can see it here on this brain MRI. It is composed of 4 parts: the rostrum, you see here, the genu, the body, and the splenium. So it has a role in integrating the motor and sensory information from the 2 sides of the body, and it plays an important role in higher cognitive functions, including social interaction, language, processing speed, and also motor coordination. So agenesis of the corpus callosum, and so more broadly, defects or malformation of the corpus callosum, so I will also say ACC during my presentation, are among the most frequent viable brain malformation, affecting 1 out of 4,000 newborns. So you can see here again the normal corpus callosum. Here you can see an individual without corpus callosum, so a complete agenesis of the corpus callosum. And here you can see a part of it, so the anterior part is present, but you can see that the part of the body and the splenium is missing, so corresponding to a partial agenesis of the corpus callosum, or also called hypogenesis. Oh. So, but there is a spectrum of malformation, and you can imagine that you have different types of malformation, including funny-looking corpus callosum like this one, called dysplastic or dysmorphic. You have also corpus callosum that are fully formed, but are thinner, like this one. This is called corpus callosum hypoplasia. And you have also thicker corpus callosum, like you can see here. You cannot see the pointer because I'm not using the keyboard. So here you can see the thicker corpus callosum, which is a very rare condition. So I said it's a frequent brain malformation, and it's even more frequent in children with intellectual disabilities. So it's present in about 2 to 6% of children with this condition. It usually occurs sporadically, so there is no family history of brain malformation or agenesis of the corpus callosum in the parents or in other family members. And it is a highly heterogeneous condition that can occur either in isolation, so only this brain malformation is present, or it can be also associated with other cerebral or extracerebral malformation. So among the cerebral malformation, the more frequent ones are cerebral hypoplasia, Dandy Walker, holoprosencephaly, schizocephaly, lissencephaly, heterotopia, and so on and so forth. And among the extracerebral malformation, you have cardiac malformation, anomalies of the urinary genital tracts, skeletal defects, facial dimorphism, and it's just a short list. And of course, these heterous conditions are related to multiple causes and etiologies. So usually, agenesis of the corpus callosum results from a disruption of the development of the corpus callosum, at least one of the essential steps. So you can see here very briefly the different steps that leads to the formation of the corpus callosum, which forms around or between the 10th to 20th weeks of the pregnancy, as you can see here. But of course, you need all the steps before. So of course, if the neurons have not migrated in the right layers, they cannot send out the axons that will form the corpus callosum. So actually, the axons have to go through the midline, and this is there are several molecules guiding these axons. This is a process known as axonal guidance, and all the pathways that are relevant to corpus callosum formation have been beautifully reviewed by Tim Edwards and Linda Richards in this their brain review paper. So just to say that the corpus callosum is not fully myelinated at birth, and it will continue to be myelinated after birth. So among the causes of agenesis of the corpus callosum, you can find maternal environmental factor like prenatal exposure to alcohol, drugs like cocaine, and also viruses. So the most important cause is infection by cytomegalovirus. Maternal diabetes has been also associated with malformation of the corpus callosum, and although there are not yet really factors that are known to cause agenesis of the corpus callosum, probably it is probable that nutritional deficiency in the mother can also be associated. And I just want to mention that sometimes the agenesis or the malformation is due to a structural blockage. So, for example, a cyst or a lipoma is present and prevent the corpus callosum to form. There are also chromosome abnormalities that are associated with ACC and represent between 5 and 15%. And among the most frequent causes are trisomies, trisomy 13, 18, and mosaic trisomy 8. And also many different copy number variations, and you will see that later on. So I've said that already, but there are many different Mendelian conditions that are associated with agenesis of the corpus callosum and represent around 25–40%. And if you look in OMIM, there are more than 400 syndromes that are associated with malformation of the corpus callosum. But in most cases, almost all cases actually, this corresponds to what I would call complex agenesis of the corpus callosum, meaning that there are other brain malformation or malformation or other organs or intellectual disability syndrome. So this is just a very short list of Mendelian conditions that are associated with agenesis of the corpus callosum. So these conditions are divided into two different types: the recognizable genetic syndrome like acrocallosal syndrome, genitopatellar syndrome. Some of them have genes that have been identified. Some, like Aicardi syndrome, have no cause yet identified. And on the other hand, you have also metabolic disorders that are associated with malformation or absence of the corpus, like callosum, with high penetrance. And usually, these are neurodegenerative conditions. So now we reach the purposes of this session. So how agenesis of the corpus callosum is detected. In most developed countries, since the 1980s, it's detected prenatally from the second trimester of the pregnancy around the 20th week. But in some cases, for individuals born before 1980s or individuals born in countries where ultrasounds are not performed routinely, we can also detect this condition postnatally in the context of a developmental delay or intellectual disability syndrome, or incidentally. You will see that later on. So when an agenesis of the corpus callosum is detected by the ultrasound, then there is different tests that are performed, usually screening for viral infection, karyotyping, and microarrays. The family is seen by a geneticist who assesses the family history and proposes to the parents to perform a brain MRI to see if the corpus callosum is normal or not. And what we do in France and probably also in all other European countries to perform a fetal MRI to determine whether this malformation is isolated or whether all the malformations are present in the fetus. If other malformations are detected, usually the risk of intellectual disability is really very high, so almost 100%, and also other comorbidities like epilepsy. If the agenesis of the corpus callosum is isolated, then the prognosis remains uncertain. And you can see on this schematics here that retrospective study has shown that around between 66 and 84 individuals with isolated ACC will have normal intelligence, whereas the remaining 30% will have an intellectual disability syndrome that can be either moderate or severe. So there is a real issue here, and it's really important to try to improve this prognosis. So, of course, you can imagine that it's very difficult for families with this situation, and there are also very frequent inequalities. And the first one is always related to prenatal testing. So usually, as I said, you have amniocentesis, karyotyping, macroarrays, but so far there is no or unequal access to next generation sequencing, meaning that the prognostication or the decision to continue or terminate the pregnancy is made based on the statistical risk, so the cause of the malformation is not known when the choice is made. Then there is another thing that I want to mention is that, of course, if you say to a family that they have a high risk of intellectual disability, they will probably decide to terminate the pregnancy. If you say to the family that they have a high chance that the fetus will have a normal outcome, then they will probably decide to continue the pregnancy. So, of course, the genetic counseling is really important, and it can differ from one clinician to the other, and of course it can drive a different attitude from the parents. Then the last thing that I want to mention is that if the family decides to do a medical termination of the pregnancy, which is legal in some countries but illegal or forbidden in others like Brazil, it's just not to take a pill. It's a real feticide because we are very late in the pregnancy, and of course it's very difficult, and it is related to the religious belief of many individuals, the family, but not only. And I want to mention that ACC is the first cause of late termination of pregnancy for brain malformation. So I will continue and show you the results that we had on the French project. So I personally joined the this project in 2012, but it has been initiated before by two different groups, Tania Atier-Bitak at Hôpital Necker and Delphine Néron and Marie-Laure Moutal at Hôpital Pitié-Salpêtrière and Hôpital Trousseau in Paris. Tania collected fetuses who underwent termination of the pregnancy, while Delphine and Marie-Laure followed the patients that were born after a prenatal diagnosis of ACC, and they also developed a network of clinicians who collected patients with isolated ACC or ACC and intellectual disability. So the genetic part was we performed in both centers microarrays, so different types, RACGH or SNP microarrays. We performed first an analysis of the genes that were known to be associated with ACC. So it was the callosum panel, which contains 423 genes that was designed by Tania. And we rapidly moved to exome sequencing in trios. And this is still ongoing. And since 2012, we also performed a prospective analysis started from prenatal diagnosis. So the fetal study has been published, or part of it has been published almost 2 years ago now. It included 138 fetuses, and most of them had no diagnosis at the time of the pregnancy termination. And I wanted to show you a bit, because you can see here that the isolated ACC, so at the stage of imaging before abortion, there was 40 fetuses with isolated agenesis, while after autopsy, there was only 16 fetuses with isolated ACC, meaning that we miss a lot of other malformations or other associated features by imaging. The cause was identified in 42%, so in two cases, there was one case with CMV infection, one case of maternal diabetes. The chromosomal abnormalities represent around 17%, and the Mendelian conditions you can see here were divided between de novo, recessive, and X-linked. And all diagnoses except one were done in associated or complex ACC, and you can see, I hope you can see because it's very small here, that there is a high frequency of tubulinopathies, or mutations in the tubulin encoding genes. So in the cohort of patients with ACC and ID, we have found a lot of pathogenic CNVs, and there was previous studies published, including the study of Bill and Elliot Chair, and the study of Tania. And in our own study, we had found 13% of pathogenic CNVs, and most of them were already associated with the ACC in the literature, and so all of them except the ones in orange that were new. And I will highlight two of these pathogenic CNVs. So the first recurrent CNV is the inverted duplication deletion of the short arm of chromosome 8, which is the most frequent micro-rearrangement identified in patients with ACC and ID. It's almost always associated with a developmental delay and intellectual disability that ranges from mild to severe, and other features including hypotonia, which or hypertonia in older patients, facial dysmorphia, you can see it here, and also variable cardiac, ocular, and renal malformations. And actually, it depends on the size of the deletion of and the duplication and the malformation of the corpus callosum, as can be shown in the paper from Elliot Chair and Bill comes from the duplication, not from the deletion, but the duplication of the region 8p1 to 1.23. The second recurrent CNV found in patients with ACC is the terminal deletion of chromosome 1q. It's a region of about 10 megabases that contains many genes, but only 3 of them are intolerant to haploinsufficiency. You can see them here in color. AKT3, ZBTB18, and HNRNPU. And we have collected patients with different sizes of deletion encompassing at least one of these genes. And we were able to show that AKT3 is the main gene driving the brain size. ZBTB18 is the main gene accounting for degenesis of the corpus callosum. HNRNPU is the main gene accounting for the seizures. But there are also some interactions, and HNRNPU also account for thin corpus callosum. ZBTB18 can also worsen the brain size phenotype. And although HNRNPU is the main gene contributing to intellectual disability, ZBTB18 also contributes to this phenotype. You can see here the shape or morphology of the corpus callosum in patients with both point mutations and deletions. So here are patients with point mutation in HNRNPU. You see that the corpus callosum is almost fully formed, but it's thin. Here are the patients with mutation in ZBTB18. So you can see that the corpus callosum is not fully formed. So part of it is missing. It can be the posterior part or the anterior part. And you can see the additive effects of deletion of the 3 genes in this patient who has almost a complete genesis of the corpus callosum. So coming now to the next generation sequencing results. So we had 20% of pathogenic variations in with the callosum panel, which was quite good actually. And moving to the exome in trios, we had 36% of pathogenic variants. And so both studies have done in patients with AD and ACC, and we also included several families with isolated ACC, and we have reported that 1 gene, and analysis of other candidates are still ongoing. So the main result from the callosum study was that we identified 10 patients out of 100 with de novo variants in ARIDIB. So if you had listened to the presentation of Dr. Santon earlier this afternoon, maybe you know that patients with ARID1B mutation have corpus callosum abnormality in 43%. And so if we go back retrospectively, most of these patients had features that were compatible with coffin cirrus, although they did not present the typical hypoplasia of the nail and the phalanx of the 5th finger or toe. And you can see here that the malformation of the corpus callosum found in this patient are really variable. So in many of them, you have a complete agenesis. Sometimes you have a part that remains. Some of them have a funny looking corpus callosum. Some have a thin corpus callosum, and even one has a thicker corpus callosum. So the whole spectrum is represented. So you probably know already that ARID1B encodes a subunit of the SNP complex, which acts as a chromatin remodeler. So this is another example of diagnostic that we made in fetuses. It's one of the rare family that we for which we run an exome in our lab. Actually, this family had partial agenesis of the corpus callosum that was detected prenatally, and the family decided to do a medical abortion twice, because the male fetuses had this condition. And we analyzed the quatuor, and we have found a compound heterozygous missense variance in IMPD2. So IMPD2 encodes the adenosine monophosphate deaminase 2, which is an enzyme converting adenosine monophosphate into inosine monophosphate. So it's involved in the purine metabolism. And it has been described by the group of Joseph Gleason in 2013 to cause a neurodegenerative disorder that is characterized by postnatal microcephaly, progressive spasticity, severe developmental delay without any motor skill acquisition, and also epilepsy, central visual impairment. And there is a sign that is very typical of this disorder that you can perhaps see here. I cannot see it on my slide, actually. Here, it's like a 8 number, which is at the level of the midbrain. So what I wanted to say actually on this slide is that sometimes it's difficult to make the difference between disruption of a developmental step and a very early neurodegenerative disorder. Then I will also tell you the story of this family. So it was actually it was a family that both wished to live a normal life. They had mild learning difficulties when they were children. So the problem is this woman here, she is a bit slow when performing a task, but still she holds a bachelor degree in history. And because both of them had headaches, they underwent a brain MRI revealing a complete agenesis of the corpus callosum in both of them. So the sister got pregnant, and she had a prenatal diagnosis of complete agenesis of the corpus callosum in a female fetus, as you can see here, and she was born, given the family history, and then the family history revealed other cases of agenesis of the corpus callosum. So what we did, we performed a linkage analysis first, using SNP microarrays. Of course, it was not completely informative. And then we combined this with exome sequencing. And there was only 2 variants in the regions that had a positive load score, including a frame shift variance in the gene called DCC. DCC encodes the receptor for E13.1, and it is very well known to act as axon guidance cues for guiding the axons toward the midline. So it was the perfect candidate. And it was also known that both DCC and E13.1 deficient mice has complete agenesis of the corpus callosum, as you can see here. So it's the corpus callosum of the mice, and you can see it's completely disrupted here. It's DCC and E13.1. But actually, we knew that mutation in DCC already caused another condition named congenital mirror movements. And actually, we contributed to describe patients with mirror movements. So as you can see here, mirror movements are involuntary movements performed on one side of the body that are identical and synchronous to movement performed voluntarily on the other side. So you can see this. You can see here. So it's a benign condition. These affect mainly the upper limbs and mainly the hands. And so the intelligence is normal in these patients, and they live a normal life, but it's difficult to have a bimanual, so to perform different movements with the hands, so they cannot play piano, for example. Okay. Can I stop it? Yes. Here we go. So, of course, because we had already identified DCC variants in families, we came back to these families, and we wanted to assess whether some individuals in this family had also malformation of the corpus callosum. And as you can see here, in this family with a non-sub variant, we had 2 individuals with agenesis of the corpus callosum. Then we screened the gene in sporadic cases with isolated ACC, and we were able to find variants, missense variants, in 4 families. And we were in contact with 2 Australian groups, the groups of Paul Lockhart in Melbourne and the group of Linda Richards in Brisbane, who had also identified families with both mirror movements and agenesis of the corpus callosum. So you see here in this family, all 4 affected members have both conditions. And here in this family, you have mirror movements in the females and agenesis of the corpus callosum and mirror movements in this male. So, of course, we were interested in trying to find the factors that were able to modify the phenotypes. So first, we looked at the mutation itself to see whether the spectrum of mutation was the same in mirror movements and agenesis of the corpus callosum. And it was approximately the same. So we had the impression that the missense variant clustered for agenesis of the corpus callosum in the natrin binding domain. And this was also confirmed by comparison of the frequency of variants located in this region in our population of patients with agenesis of the corpus callosum and the exact population. So this was really very significant. And we have also performed in collaboration with Charles Gallia protein modeling of the effect of the mutation on the structure of the protein. And at least 2 of them were predicted to disrupt the interaction with netrin-1. So they were located at the interface of the interaction with netrin-1. But overall, the spectrum was not different, and there was this specific mutation here that was associated with both conditions. Then we looked at the pedigrees, and by looking at the pedigrees, especially those published by Miriam Srour and Giroulo, and our pedigrees, we had the impression that there were more females with agenesis of the corpus callosum and more males with mirror movements. So we quantified this by looking at all the individuals available with DCC mutation. And this was true actually for truncating mutation. You can see that it was significant. So we had only a few males in blue with agenesis of the corpus callosum associated with truncating DCC mutations, while most of the males had mirror movements. And because there was in the literature a debate about the effect of testosterone on the morphology of the corpus callosum, given the penetrance as seen different for males and females for ACC, we looked at the effects of testosterone on the expression of DCC, and we were able to show that the testosterone has a very slight but significant effect and increases the expression of DCC. So it made us postulate that ACC is related to a threshold or different quantity of DCC during development. So of course, if you If you have 2 copies, you have more DCC or a normal amount of DCC. If you have only 1 copy, if you are a female, you have a bit less DCC expressed than if you are a male. But probably this is too simplified, too simplistic, because actually mirror movements were shown to be a defect from the cortical spinal tract, which is a different tract compared to callosal tract. So you can see here the cortical spinal tract in blue, the callosal tract in red. This is to show here that in individuals with mirror movements, you have a defect of crossing of the corticospinal tract. And actually, these individuals have the ipsilateral tract, so the tract that does not cross, which is thicker than the crossed tract, which is abnormal. So in normal individuals, you have a decussation and a crossing of the corticospinal tract at the level of the pons. And it has been shown that the callosal tracts and the corticospinal tracts pass the midline a bit differently, and that DCC and E13.1 acts differently to make them pass the midline. So probably it's too simplistic. It seems more complicated than that, and we don't know exactly all the modifiers that can determine this phenotype. So just to mention that our paper was published back-to-back with another paper from the group of Tim Yu, Christopher Walsh, and Elizabeth Hengel, and they showed that Biallelic, so recessive DCC mutation on both alleles, cause a syndrome that they call split brain. So split brain, meaning that there are no commissures between these 2 hemispheres, and also several other commissures at different levels of the of the cortical tract and so on are not present in the individuals, and it's a more severe condition, as you can imagine, and these individuals have all intellectual disability, and they also have horizontal gait palsy and a very severe scoliosis. So I've shown you that malformation of the corpus callosum are a very heterogeneous group of disorders with very extreme genetic heterogeneity. Actually, we think that specific pathways are altered in agenesis of the corpus callosum, and mainly chromatin remodeling, transcription factors, neuronal migration, and cytoskeleton, axon guidance, and also metabolism. And the penetrance of ACC is mostly incomplete for most genes and loci, and it probably the nature of the modifiers, the genetic interaction driving the phenotype remains largely unknown, so we have a lot to do. We think that complex agenesis of the corpus callosum may be more is mainly monogenic, while isolated ACC is probably more polygenic condition. So in prenatal situation, ACC can be the first sign of a developmental delay or intellectual disability syndrome, but it can also be associated with a quite a benign outcome. So I don't say that the person without corpus callosum are completely normal. So if you do really tests, you can see that they are slower to perform tasks. They have some learning disabilities, but this is in the normal range of intellectual intelligence. So predicting the outcome remains a challenge in clinical practice. And so I've showed you that if we find other malformations, then the risk is very high that it's the first sign of a very severe or moderately severe syndrome. But if it's isolated, there is still the risk that something is not seen, like hypertrichosis, for example. And of course, we would like to improve our capacity to make the prognostic, and we will introduce next generation sequencing and exome sequencing in trios in the next few. Actually, it will begin now. So I thank you for your attention. I think I have mentioned all the collaborators that have done the work, so mainly Delphine Héron and Marie-Laure Motard for the clinical part, Solveig Eide, who did his master and then continues on this subject for his PhD, Boris Keren, who did all the chromosomal work, Caroline Nava and Agnes, who were involved in the next generation sequencing. And of course, this is a work done by, we could not have done this work without our collaborators, and we are also very happy to be part of the IRC5 consortium, because it's important to work together to improve the diagnostics for this condition. Thank you.